Welcome everybody to the special year seminar on theoretical machine learning at the Institute for Advanced Study. Today, we are delighted to have a scientist as distinguished as Professor Sanjeev Arora as our speaker. Sanjeev is the Charles Fitzmaurice Professor of Computer Science at Princeton University and also a distinguished visiting professor at the Institute. Sanjeev is known for his transformational contributions to the theory of computational hardness of approximation. He was behind landmark results developed during his PhD that showed every problem in MP has probabilistically checkable proofs of sublogarithmic query complexity, and later on constant query complexity. This later result came to be known as the PCP theorem, which is recognized as the most important result in computational complexity theory since the Cook-Levin theorem. He received the Gödel Prize for this contribution in 2001 and again in 2010 for another breakthrough in the approximation of Euclidean traveling salesman problem. Recently, he has turned his attention to machine learning and has been a leader in the theory of deep learning. He was recognized with the ACM Doctoral Dissertation Award, a Distinguished Alumnus Award from UC Berkeley, the Fulkerson Prize, Best Paper Awards at Stocks and Fox, the ACM Infosys Foundation Award in Computer Sciences, and is a fellow of the ACM and a member of the National Academy of Science and the American Academy of Arts and Sciences. Please welcome Sanjeev Arora.
Thank you. The title is Instahide, Instance Hiding Schemes for Private Distributed Learning. And this is joint work with Yang-Sibo Huang, who is the lead author, Zhao Zong, Kai Li, and Kai is a colleague at Princeton. As the title suggests, it's about private distributed learning, where multiple parties with private data want to collaboratively train a deep model. So for example, hospitals with patient data or groups of users wishing to train a language model using text messages. So the naive way to do it, the naive idea would be to pool all data to the central server, which then does the training. So here you see these hospitals which had a store of data, and there's a central server, let's say AWS, and they just ship their data to AWS and let it do the deep learning. Well, this violates privacy laws such as HIPAA, which govern hospital data, patient data. So this is not, and also we users who want, say, Amazon to use our data to train some model that's useful to us would not want to ship over our data to them, ideally. So actually, you can think of the speakers, the Alexa speakers, and so on. You could try to hold on to that data instead of sharing it with Amazon. All right, so federated learning is a framework for doing this kind of distributed learning, where all parties participate in the training. So they are all doing model updates using their data, and they share the model updates, that is the gradients, computed using their data. So they batch their data, and then they do batch gradients for their data and send it to the server, which sums up the gradients to get the average gradient. So that's federated learning, and it's widely deployed now, also for Internet of Things and so on. But sharing even batch data leads to privacy leakage, because it turns out that using gradient matching attacks, as in this paper of Zhu et al., attackers can reverse engineer the private input of the hospital from the shared gradients. And this gradient matching attack is just very simple. You know, the unknown is the input, and you're trying to solve for that unknown so that the gradients from that unknown input match what you're observing. And that turns out works. Okay, so that's not very secure, just vanilla federated learning. So then there are other frameworks for introducing some level of privacy. So a famous one is differential privacy. where you add noise to the gradient. So instead of sharing the gradient computed using your private input, you add noise to it according to the differential privacy theory. And now to bound how much privacy is being lost, you have to do a careful calculation as you do the training. And that calculation may suggest increasing or decreasing the noise. And so that's all explained in this very important work of Abadi et al. But there are significant shortcomings. So there's a big accuracy drop on CFAR10. And this accuracy drop comes after extensive pre-training. So you've already pre-trained using unlabeled data, and then you have to train very little on the labeled data. And even then you have to add so much noise to it that you have a huge huge accuracy drop. And there's also some efficiency hit. The other more significant downside is that it bounds privacy loss due to the release of the trained model. That is proper use of the shared gradients. So you're sending the gradients to the server, and nobody is eavesdropping there, just the server takes the gradients and adds them up. If you do something else with the gradients, like the gradient matching attack, there's no bound on how much privacy could be lost. All right, the other game in town is cryptography-based solutions. Now, this is a highly developed field. You know, every time we do any e-commerce, this is getting used. And so there's been 45 plus years of research in this field, and it gives candidate solutions for almost all conceivable settings. And I emphasize the word candidate because these are not always solutions that are very efficient. Okay, but setting that aside, the idea in a cryptography-based solution is that privacy violation requires the attacker to solve a computationally difficult problem. And this computationally difficult problem is, of course, only conjectured to be computationally difficult. Proving that it's actually computationally difficult would also show P is not equal to NP. So that's an open problem. So it's only a conjectured computationally difficult problem. So that's the game in cryptography. And we'll see the solutions that are being suggested. But what I want to emphasize is that cryptography and differential privacy are not directly comparable. They are sort of complementary. So the differential privacy guarantee seems fairly weak. And yet, even so, crypto solutions may not satisfy the differential privacy guarantee. And secondly, the crypto base is based on complexity conjectures, as I mentioned above, and differential privacy is not. It's unconditional. So they're kind of not directly comparable. They're different games. All right, so how is cryptography used in this federated learning setting? So it turns out that you can compute on encrypted data, because deep learning is just doing some kind of addition, multiplication, threshold, ReLU, etc. These operations on encrypted data. Okay, a sequence of such operations. And those can be done on encrypted data. And there are solutions going back to the 80s. And the modern solution is a fully homomorphic encryption of Gentry and many other papers. The downside of cryptography, as I already mentioned, is there's a huge efficiency loss often. And you really can't do deep learning with fully homomorphic encryption. And also it requires special setup, like a public key infrastructure, finite field arithmetic, etc. You can't just plug it into PyTorch as is. By the way, I want to note that there are more efficient implementations just for the gradient aggregation problem. For example, Pilutla et al. But there are other papers as well. I'll probably pause here and take any questions, because I'm now going to move on to what we do. Any questions?
If you have any questions, you can feel free to unmute yourself or type in the chat box. Okay, I guess we don't have any questions.
Okay. So now we come to our solution, Instahide. So on the left and right, you see cryptography and differential privacy, two other the popular solutions I mentioned. And with cryptography, the significant issue is the efficiency loss. And with differential privacy, the training accuracy suffers. You train this model, but because you've added so much noise to the gradient, the final accuracy is actually not very good. So Instahide is a new cryptographic method. It's a new encryption of the data. But in contrast to the earlier cryptographic solutions, you can take this encrypted images and do deep learning directly with them. So Python doesn't need to know these are encrypted in whatever way. It just treats them like images, right? Pixels, and it just does deep learning on them. Usual architecture, nothing changes. And it gets fairly good privacy without slowing down training or significantly reducing accuracy. It reduces a little bit, but not too much. 2, 3, 4%. Okay, so the picture here is everybody applies this encryption on their input and then just uses it in federated learning. Now I emphasize, as I mentioned earlier already, the server runs standard deep learning, no specialized operations or overhead. And it avoids the efficiency loss of earlier crypto solutions and the accuracy loss of differential privacy. Just repeating myself, but emphasizing those two things. Kerr, feel free to stop me if there are any questions now.
Sure, I don't think we have any.
Okay, all right.
So the question is from Ryan Rogers. The question is, how does the crypto approach ensure privacy of the final model?
Yeah, so we'll get to that. Okay. Oh, no, it does not ensure, it does not, as I said, cryptographic approaches do not give a differential privacy guarantee. Did I answer your question?
Ryan, feel free to unmute yourself if you have follow-up questions. Okay, I guess not.
Okay, so we'll come later to what kind of privacy. So the privacy is just that they cannot reconstruct the input X, information about X. So you're using an encrypted version of the input. They don't learn anything about your input, except what's revealed by the classification, right? Whatever the model reveals. So you could always, with cryptography, try to use differential privacy. But as I said, to get any kind of provable bounds on privacy leakage, the noise has to be so high that the accuracy suffers. Okay, so this guarantee is similar to cryptography, privacy guarantee.
We have another question from Varun. The question is, if the server has no efficiency loss, what about the clients?
Oh, so clients, it's a very simple encryption. I'll show it to you. It's basically, very, very simple operations. I mean, it's negligible overhead. Okay,
and we actually just got another question from Abhishek. And the question is, in differential privacy-based solutions, can we encrypt the noise and send to the server?
I don't see how that would help with privacy. I mean, it's less private, right? If you don't add the noise, you're sending the gradient in the clear. That, if anything, reveals even more information. So privacy has multiple meanings. And differential privacy, I want to emphasize, experts know this. It's a very specific notion of privacy. Like, what information is contained in the model about this input? That's the only kind of privacy it bounds. And cryptographic privacy says, you don't learn anything about the input except what the model reveals. Sort of complementary. Is this clear? If there are any experts here who want to correct any of what I said, please feel free to unmute yourself.
Okay, I guess those are all the questions.
Okay, good. So now the inspirations behind Instahide. So inspiration 1 is mix-up data augmentation. So mix-up is an amazing technique. When I first saw this 2-3 years ago, I was just blown away. So the idea is, so normally we think of deep models as non-linear, non-convex, blah, blah. Well, mix-up turns that intuition on its head. It says, I'm going to do deep learning, but along the way, I'm going to teach deep models to behave linearly on the training data. So what does that mean? So you're thinking of images as vectors, okay? So there's vector addition, right? So there's a linear algebra on vectors. And the labels are also vectors. They're just one-hot vectors, right? If you have C classes, the label is 0, 0, 0 everywhere except the coordinate corresponding to the class which this input belongs to. Okay, so in Mixup, you take convex combinations of images. So you pick a random lambda between 0 and 1, and you take the mixture of two training images, x1 and x2, lambda times the first image, plus 1 minus lambda times the second image. And you do the same for the label vector. Okay, so illustrated here, there was a cat picture, 0.6 times that, plus, and there was a car picture, and 0.4 times that. And just vector addition, you get this picture. And if you squint at it, you can sort of see the cat, and you can sort of see the car. Okay, and the label is the convex combination of the two one-hot vectors. So the amazing thing is that you never train this model with vanilla images, like the unmixed images. You only train with these mixed images, pairs of images. Okay, so it's never seen a clean image. You train it with these mixed data. And nevertheless, this trained model gets better final accuracy on normal images. So at inference time, you just feed it normal images. Okay, so that's why it's called the data augmentation technique. All right. So by the way, Koya, feel free to interrupt me wherever there are questions, because I don't think I'll take the full hour. So I saw this, and of course we've been trying to understand it. We try to understand theory of deep learning. But here's an aha moment that in the process of this project, that the takeaway I realized of Mixup is that it's okay to mess with the training data in very counterintuitive ways, right? Normally in deep learning up to 2018, data was inviolate, right? You don't mess with the data or question the data. You just input it into the training. And here you're messing with the data. Okay, and just doing deep learning on it, vanilla deep learning. So that was one inspiration. Here's a second inspiration, and that's from complexity theory. That's my previous life, as Kerr mentioned. So maybe many of you vaguely remember the subset sum problem, which is one of these NP-hard problems. So this is what's called a parameterized version of subset sum. Firstly, it's a vector subset sum, and secondly, it's parameterized. So it's just, you're going to do a sum of only k vectors. All right, so here's the problem. There's a set of n public vectors, which everybody knows, v1 through vn. And the problem instance is generated by picking k secret indices, I1 through ik, and to release the sum of the corresponding vectors, the corresponding k vectors. Okay, so now these vectors were picked, the k1s, and then you just added them up. Now, the vector subset sum problem is to untangle it, right? Figure out which vectors were used. And this is conjectured to be a hard problem, and something called the exponential time hypothesis, which is a stronger version of P versus NP, says that finding these unknown indices requires n to the k over 2 time. Okay, and this holds even for small k. So k equals 4 by this hypothesis would already be pretty hard, right? Because n is fairly large. Let's say you're looking at ImageNet. Okay, I didn't even talk about it. Let's say ImageNet sizes, so 10 million things, n is 10 million. Quadratic in 10 million is already pretty large, right? So even for very small k, you start getting hard problems here. Okay, so that's a vector subset sum problem. Any questions about it?
No, I think there are.
Okay. So now you're wondering, okay, where am I going with this? So we had vector sums in Mixup, and now we have the vector subset sum, right? So you're wondering, wait, just plain Mixup, right? What we had on the previous slide already ensure privacy, that you mix up images and it sort of hides the image. Well, we already saw in the last slide it doesn't, and here's another image. Here's another picture. Dog and horse. You added the two images. You can still sort of see the horse and this dog. And so indeed, just summing up 4 or 5 images is not going to hide them, because the computational hardness here, like all NP completeness theory, is about worst case vectors or worst case instances, and images are not worst case. So mix-up alone does not ensure privacy in the sense we're talking about. You can recover which images were mixed, or sort of recover. Okay, and I'll sketch this later. All right, so inspiration 3. So those were 2 inspirations, right, about vector sum. This is about something else. So this is instance hiding in the cryptographic sets, and it's done over finite fields. This is classic in cryptography, and it led to all kinds of other ideas, PCPs, which Kerr mentioned earlier, learning with errors, lattice-based crypto, fully homomorphic encryption, etc. So similar ideas occur in all of this cryptographic settings. So the idea is the following. So there's some secret input X, which is over a finite field with Q elements, and it's d-dimensional. So that's X. So it's secret. You're trying to hide it. R is a random vector, which you pick. Okay, and everybody knows you're picking a random vector. So same vector space, okay, over finite field of size Q, d dimensions. Now, X plus R is a random element. Just because R is a random element, X plus R is also a random element. They are not, it's not uncorrelated with R, but it is distributed like a random element. So for somebody who doesn't know X or doesn't know R, X plus R just looks like a random element. Okay, it hides X. Very simple idea. Okay, it's obvious idea. And it's a random element just because it's a group, right? So just property of group addition. Now, I mentioned this idea as an inspiration, and you're thinking, okay, then we want to avoid finite field arithmetic, right? I mentioned that that's kind of cumbersome in deep learning. Well, so we're not going to use finite field arithmetic, but we're going to use the special case of this fact, this instantiating fact, over the field of 2 elements, GF2, which has only 2 elements, 0 and 1, and the addition over GF2, right? If it turns out is isomorphic to multiplication over this other group of +1 and -1. It's also a field of 2 elements, but the operation is multiplication. So there's an isomorphism between these 2 groups of size 2. Okay. So if you haven't seen it, just take my word for it. Simple to verify. Just verify all the 4 things you have to verify. And now adding a random vector to a R to a vector X is analogous to, or is akin to, randomly flipping the sign of each coordinate. Okay, because that's like multiplying by +1 or -1. If you multiply by +1, you haven't flipped the sign. If you multiply by -1, you flip the sign. Okay, so it's you can think of it as multiplicative noise. So this parity, I mean, it is all standard. That parity is kind of like multiplicative noise. So parity is just addition modulo 2. So let's think in terms of pixels, the vectors we were talking about, right? So we're talking about images as vectors. So so coordinates are pixels, and let's say pixels are now real numbers. A random Sine flip actually changes the pixel value, right? The pixel color. So like if you had a pixel 0.5, 0.5, 0.5, that's light gray. If you randomly flip the sign, you can get 8 possibilities, right? One of them is unchanged, but the other 7 are changed. And for instance, if you flip the first coordinate, it's actually lake blue color. So the color of the pixel changes, and there are 7 possibilities. Okay, so we're going to use this operation, the Sine flip. All right, so now here's Instahide, ready to describe it. We're trying to encrypt a private image, like this cat image. And roughly the idea is that you're going to mix with images from a public data set, like ImageNet. So here's a private image with a training set. There's a large public data set of images. You pick an image from there. So now that's unlabeled. I mean, okay, ImageNet does have labels, but you could use Instagram images or anything. And so this is unlabeled. And now, for example, you're mixing, so you take 0.6 times the first plus 0.4 times the second, as we did before, and you get this mixed image. And you can see the cat and the bird in there. And the label of this image is cat again, okay? Because the cat was the training image. And now you're going to do this private one-time key, which randomly flips a sign, okay? So you randomly, with probability half, flip each sign. So each pixel is an RGB value. Each of those you flip with probability half. So now you get this new image, which looks like garbage, right? Noise. So this is your training image on the right that you input into PyTorch or whatever framework you're using. This label and this image. Any questions?
So, I mean, I have one question. So the private key is specific to each example or the entire
Each
data?
image, correct. Yeah, and you can encrypt the image again for a second batch. So we actually encrypt a few times with a new encryption.
So we have a question from Sohail Faisi. What happens if...
Sorry, you cut out.
Oh, what to the red?
Sorry, again cut out.
Oh, so what happens if you don't apply the mix-up and only apply
we'll talk about it. Yeah. So I'll address all this. Yeah, both components are important. So one comment is, mixing with a public data set. So firstly, I mentioned here, public so that it's off the shelf, right? Everybody can use it, no special preparation or handshaking, right? Just some large data set. And it's large because it gives more security, right? Like vector K-sum, like you're mixing from a large set of possibilities. So now, mixing with this image from the public data set, like that's a lot of noise, right? 0.4 times this image, which you're adding to 0.6 times the cat. So you're mixing in a lot of noise, okay? Even in this simple example. So it is kind of like differential privacy, right? You're noising each pixel a lot, plus you're doing the Sine Flip. They're both types of noise and they're both important. Without that, there are attacks. Okay, I'll talk about this later.
Okay, so we also have many questions, actually. So the first is from Oscar. So the question is, if we consider the encrypted input as the image and categorization with the unencrypted labels, does that mean you do the same encryption at the edge? So if the edge is not powerful or identical hardware, does the method fail?
Wait, you're assuming the edge cannot do vector addition? Or that it doesn't have the public data set? I mean, it can, the edge can just sample, if you have 1,000 training images, it needs 10,000 random images from the public data set, which it can just have offline.
Okay. And the second question is from Varun. So why are we not mixing the labels?
There's no label. This public data set has no labels. It's random images, unlabeled. I said ImageNet, but you can think of anything, any image set.
Okay, so I guess the question is, if we were to do classification, for example, from...
Okay, look at the bottom. So it's also fine to mix within the training set. Let me actually go to the next slide. I'll give you the full thing. As I said, this is just the idea, but it is possible to mix within the training set completely, which is not as secure, but if the training set is large enough, it's probably fairly secure. Right. So you could do that too. Okay, so here's a full description, all right? So this is with mixing parameter K, think of K as 4. So you're going to mix with K over 2 training images, exactly what the question was asking. You can mix within the training data set and mix with K over 2 public images, followed by pixel-wise random Sine Flip. So I hope that answered the question. And mixing within the training set is good because it's a data augmentation technique. So if I'm going to compare to state-of-the-art classification algorithms which use data augmentation, I better allow that in here. You can also do data augmentation after encryption and so on, but I won't go into that. So any questions now? Yeah, so now this is the full.
All right. We do have many questions.
Okay.
The next question is from Ryan Robbins, who asks, does each device or hospital have the same public images? How many do you?
No. It's a random sample, right? I mean, let's say they have 1,000 training images and they have some number of epochs, I don't know, 100. You take 10,000 roughly public images and just store them.
Okay, so the next question is from Vishnu Bobetti, who asked, is the encryption key the same for every cat image from each user?
No, so for every image you use a new encryption key. So I'll write that here. The secret key, I should have put this up. Yeah, it was on the slide. The secret key for encryption is a choice of images used for mixing. So if you're mixing the cat, you also mix it with car, which is another one of the training images, plus these other two, the bird and the flower. Those are the images you mix with. That's part of the secret key. And the random sign mask you use for this cat in this epoch. It's never reused during training. I should have put that up earlier, sorry.
Okay, thank you. The next question is from Reza Zafrani, who asks, do the public images create an issue if there's some level of similarity with the cat image?
As I said, I think it's probably secure even with a large enough training set. But yeah, I mean, we're assuming these images are distinct, right? I mean, they're not. What's the chance that if you take 10,000 Instagram images, any of them is similar to yours? So yeah, I mean, that's always the case with any random number generator based methods, which are all cryptography methods, that there's some small chance your seed is wrong or something.
Mm-hmm. Thank you. The next question is from Taha Togani, and the question is the role of the public images like the public key role in cryptography?
It's still a private key, so the public, as I emphasized, the reason is because we want to have a solution that you can deploy off the shelf, right? No handshaking needed or anything. So that's the only reason. But it's not public key in the sense of public key cryptography because you never make it public. It stays private. So it's it's more like a random oracle, if you know that in cryptography. So it's all out in the public. It's stored somewhere. You take some random pieces out of this oracle, and you use that. So it's more like a random oracle.
Thank you. So the next question is from Rohit Goswami. The question is it necessary to use images?
Oh, very good question. Does it apply to other types of data? Yes, but I'm not going to talk about it because, yeah, those papers are under review and so on. So, yeah.
Thank you. The next question is from Varun. So the question is, does the training data set size increase because of the mixing? And can the mixing images be reused as many times as needed?
Does the training data set size what?
Does the
Sorry, you cut out.
So do you have to train on more? Oh, sorry. Guess let me rephrase. Do you have to train on more images because of the mix-up?
No. Yeah, I'll have some more images. I'm not sure, more encrypted images. Yeah, you encrypt for every epoch, a new encryption. So, but I'll show you you train on CFAR10 and we'll measure the accuracy loss. So okay, yeah, you don't need any more training images. You may lose a little accuracy. Maybe that's right. What the question is getting at. Yeah.
Right. So the next question is still from Varun. Can the mixing images be reused as many times as needed?
No, as I emphasized down there, we don't recommend reusing them. It's possibly still secure, I don't know, but I wouldn't recommend it. I mean, there's no reason to, a priori.
Okay, thank you. The next question is from Ji Wong Im, and the question is, how does the choice of lambda coefficients matter?
Yeah, they're just random between 0 and 1. And there's a slight change that with the training image, you probably want to give it somewhat reasonable coefficient. You don't want it close to 0. So I forget what it was. Maybe Yangsibo is on it was something 0.3 or 0.4 for the training image, and then the rest is noise. Yeah, rest is the other images. I forget exactly.
Thank you. The next question is from Camille, as is Shelley. The question is, can someone remind me how we choose the lambdas? I suppose.
It's a random choice between 0 and 1.
Okay.
I don't think it's very crucial. I think it'll use whatever random number generator.
Mm-hmm. Next question is from Gantavia Bass. The question is, how will flipping pixels affect the training process in terms of optimization?
So we have to go there, right? As I already promised, it doesn't affect accuracy at all. And you plug it into the standard deep learning, no change in any code. You train on these bizarre images.
Right.
Maybe I should move on. I think the questions are not so different from each other, and maybe we're answered. So let's move on, and maybe we'll have another round of questions.
Okay.
So maybe this will also help answer, right? So like this would help answer the previous question. All right, so experimental study, I'll show you various things. A, efficiency and efficacy. All right, so on this, you see on 3 standard data sets, MNIST, CFAR10, and CFAR100, and these are standard architectures, ResNet 18, NASNet. Vanilla training on the top, you see, everybody knows MNIST 99.5 or so, CFAR10 is like 95-ish, and CFAR100 is 77.9. The differential privacy approach, the best one that we would find. For MNIST, most of these work reasonably well, not much accuracy loss. But for CFAR10, it already drops to 72%. And that's after a lot of pre-training. So labeled private data, public data set labeled with labels for pre-training. And the bottom two are Instahide. If you use mixing within the private training set, if you sort of think it's large enough that that's secure, then we get it CFAR10 accuracy 92.3, which is pretty good. And if you mix with public images, and I think we use downsampled ImageNet images, 50,000 ImageNet images, then we got 90.3 accuracy. So it's like less than 5% drop in accuracy. And yeah, we're using this large unlabeled public data set for mixing. Training time increase, we're using standard deep learning on those crazy images, right? The noisy looking images. And the training time increase is minor, 5%. The time to encrypt is basically nothing. Instahide was applied during training. Whether or not you apply it during inference is up to you. It can be omitted, just like with Mixup, and that works. It's a crazy thing as far as I'm concerned. You train on these crazily encrypted images, and then at inference time, you just give it a normal image, and it gives the right answer. You can also leave it on, if you like, leave the Instahide on, and there's a minor effect on accuracy. But I want to emphasize that that has some benefits. Like if you use Instahide during inference, that's like, this crypto problem that people have been working hard on, which is, we already discussed that using cryptography during training has a huge computational overhead, like you use homomorphic encryption or something. So in this paper, like Delphi, they were doing secure evaluation only. So the model is trained and just inference on a public server via homomorphic encryption. Okay, and that already requires a lot of work. So you could use this in Instahide and no change in anything, no normal setup. Any questions here?
Yes, so we do still have a few questions left over.
Okay.
So the first is there a non-trivial probability of collision? So for example, an encrypted version of the cat's possibly equaling to an encrypted version of the dog?
No, it's tiny probability, minuscule, because of random sign change, right? That's like you're changing a d-dimensional vector randomly, flipping the sign. And not to mention even over mix-up, it's like a very tiny probability.
Thank you. The next question is from Wei Hu. The question is, what does extracting any information?
Oh, so we have to get to that, yeah. Yeah, so anything that you think will come later in the talk, just wait, yeah. Only ask questions about what you've seen.
All right, the next question is from Hongling Yuan. The question is, does the random bit flips or sine flips break the assumptions of the convolution layer? I suppose the question is asking if the convolution layer is imposing spatially invariant.
It probably does, but look at the numbers. This is a convolutional net, ResNet and NasNet. Somehow it works. This is a magic. I agree. It is crazy. I mean, I was stunned that this worked.
Okay, can I ask a quick question?
Yeah.
One thing I don't follow. So the random sine flip. So let's say it's a cat, right? You have an image of a cat, and then you have an image of another cat. The random sine flips.
It will not be an image of a cat. Oh, you mean within training? Okay, fine.
Yeah, I have two different images of cats, right?
Yeah.
And the sine flips are two different sine flips for the two of them, for the two images.
No, same sine flip. I'll go back. So here I'm encrypting the first cat image. I mix it with the car image. Could have been anything, some other, could have been from another cat class, but different image. It's not very likely to be a cat image, right? You're mixing with a random image. And then public images, and then you flip the sign of this combined input on the left. So you first do mix up, which is a huge amount of noise, and then you add this multiplicative noise. You put this multiplicative noise, the sign flip. I think what you are asking is also possible, that you can encrypt individual images and do mix up after doing the sign flips, and I didn't want to get into that. That has some accuracy loss. That's why I'm not presenting that. But that is also possible. Deep learning is amazing. It's stunning that this works.
Thank you. Now, we have two more questions. So one is from Sharan Waswani. The question is, did you investigate what features or parts of the original image the network is looking? So by using influence functions for attention.
No. So because you don't know, like those influence functions, you know, at least the good ways of doing that, right, involve looking at the image as well. I mean, I'm not sure which ones you have in mind. So, but like the saliency methods and so on, they involve looking at the image. And the adversary will not know the image that was used for mixing. So they don't have access to the input. They have access to the encrypted input. So you mean in the encrypted image or in the original image? I think you meant the encrypted image. Sure. In the encrypted, the adversary can have the encrypted image, and there it has some idea of where it was looking. Yes, correct. But, you know, yeah.
Okay, so we have a few more questions. So I think I'm gonna leave Tan's question at the end just because it's higher level. And then I'm gonna proceed to Alan's question. The question is, when you make predictions, you can either use the original image or the encrypted image with or without Instahide. Does it have any predict difference, I suppose?
Yes, as I said, there's a minor effect on accuracy. This is better without, but you can use with, and it's just a small change.
Right. And the next question is from Sharan Waswani again. The question is, in the encrypted image, then go back to, sorry, I don't know what the question is. So let's move on, and then if
maybe let's move on, and maybe it'll get answered too. Yeah. So another experiment, how accuracy changes with k, the number of mixing images. Now remember that we are conjecturing that the security improves exponentially with k, right? The subset sum kind of calculation. So So here you see for MNIST, C410 and C400. Let's look at C410, for instance. So if you use k equals 1, accuracy is 92%. K equals 2 is 94 or something. Then 3 is a little bit of drop. 4 is a little bit of drop. The reported number on the previous slide, 5 is slightly lower too. But this blue portion is 90%. So they're all above 90. And likewise for C400. So I would recommend k equals 4 is a sort of good balance. It's, if you're mixing with a large, 10 million image data set, it's probably secure enough, and the accuracy loss is modest. And the reason why k equals 1 is not as good is because mix-up is not being used in there. Here's another experimental study about security against various computational attacks. So now we get to the privacy loss that people were asking about earlier. How do you reason about privacy loss? So let's be clear what's going on here. So each party had their secret inputs, and they converted into an encrypted input, and then just plugged it into federated learning or whatever framework. So now you can think, wait, how do you reason about privacy here? That the adversary didn't learn from what he could see, the secret input, right? Anything about the secret input. Because there's all kinds of information flying around, what the other parties are sending, and gradients, and who knows what. So how do you reason about this? Now, if there are any cryptographers, they'll say easy peasy. So I'll walk you through that. So you do some kind of a thought experiment. Suppose the rest of the world is corrupt, okay? And the attacker knows everything except the secret input, knows all the inputs of the other parties and their gradients, whatever it needs, right? The model parameters, everything. So now, notice that, if you claim you have some kind of attacker, I'm going to give that attacker even all this information. Okay, so it's even more powerful. But now notice that this strengthened attacker, you gave me some attacker, I gave him this extra knowledge, right? Everything else except X. Now this more powerful attacker, actually any information gets about X during the protocol, he could have computed himself efficiently, right? Given all these inputs. So now for the cryptographers, just an aside, this is assuming some kind of a circuit model of hardness, so like it's hard not just for Python code, but also for circuits. Okay, and if you don't understand that distinction, I'm not going to go into that. Okay, but in complexity theory, that's sort of standard, or cryptography. So anyway, the attacker could have computed all this information himself, whatever he's seeing during the protocol. So therefore, we conclude that the privacy violation involving X during the protocol is upper bounded by the violation that occurs in just giving him the encrypted input X tilde. Okay? And since we're assuming that the encryption is secure, we're assuming that X tilde is hiding information about X. Okay? So an upper bound of the privacy loss about X in this entire protocol is the intuitive one, namely the loss incurred in going from X to the encrypted input X. Okay? So therefore, it suffices to look at how secure this encryption is. Any questions there? It's an obvious point for those who've ever studied any of this formally, cryptography, maybe a novel thing for others. So I'm open to questions.
Okay, any questions on this point? I'm gonna get to all the other questions on other points later. Okay, so yeah, okay, I think that's not really, so.
Okay, good. So you have an urgent question, or should I go to the other attacks first?
I think you can go to the other attacks.
Okay, all right. So we did various experiments on statistical indistinguishability. This is with a very small number of images, so that we could actually compute statistics. Probably if you have a larger set of mixing images. So here we have 1 of 10 private inputs and 2 public images, okay? So and the public images, it was a small set as well. So we're computing just, how much variation do you have in the pixels and so on. I mean, if you look at these plots, it's a little bit hard to know what to make out of this, okay, these empirical distributions of some statistics. So we ran one statistical distinguishability test for distributions, Kolmogorov-Smirnov test, and it suggests no significant difference between distributions of encryptions of different images. So the encryption seems to hide information about the image pretty well, at least statistically. So the most strong attacks are practical attacks, right? Those Kolmogorov-Smirnov are very simple attacks, right? Simple statistical tests. You could try to do more practical attacks using big amounts of deep learning. So there's a gradient matching attack for, against federated learning and federated learning with differential privacy that I mentioned earlier, Zhu et al. So there the attacker observes gradients generated by a private X and tries to construct an X star that yields similar gradients. Now notice that this is actually a stronger attacker than what Zhu et al. Considered, because there the attacker was getting batch gradients, right? So the information about X was already mixed up with the batch. Here I'm giving you directly the gradient from X, okay? So here, Mixup doesn't hide information. You can see that the reconstruction from giving the gradients actually gives you the mixed up image, and from there you can get some information about the original images. But Instahide does seem to hide the information. Now, I'm reminded that, this question earlier about saliency or influence functions or something, you do see something, right? And when it recovers, some gray pixels. I don't know what's going on there. But there were gray pixels already in Instahide. So it's hard for me to know whether it's learning anything interesting or not, okay? So on the left is the encrypted image, and on the right is what the gradient matching attack recovered. And the reason gradient matching doesn't work is that it doesn't know, what images are being used for mixing, okay? And it doesn't know the private mask, right? The bit sign flipping mask. So it doesn't know both of those. So if it knew just the mixing images, it could work. And it's a separate experiment. If it knew just the mask, it could work. But if it has both, it's very hard. Then here's another attack, deep decompose attack, which is obvious one a deep learning expert would come up with. That you train some kind of an encoder-decoder convent to decrypt. So you give it examples of encrypted input and the secret input, and say, look, this corresponds to encryption of that, right? And can you learn this mapping, right, from the encrypted input to the original input? So the obvious architecture is some kind of an encoder-decoder convolution, deconvolution, I mean. So, and whoops, sorry. So again, if you use, so here you see, if you just use one mask, it actually can recover. But if you use random masks, it doesn't recover anything. Interesting. Okay. Okay, this is just, why Mixup is not secure. So it's just sort of, you already see it in the experiments that Mixup alone is not secure, right? On the left, you see that. So I was going to give a mathematical explanation for that, but that's not as important. I'll take questions first about this. I only have 2 or 3 slides left. So yeah, I can take as many questions as time allows.
Okay, so do you want to take all the questions that are sort of not related to this slide now, or leave them?
No, so if they're sort of high-level questions, it can wait till the end. But if anything about the details of the slide so far.
I don't think there's anything that's related.
Okay. All right, so moving on, why Mixup alone is not secure, a simple explanation. Start thinking about it. So in general, we're going back to this, something like the vector subset, some kind of setting. So your database of vectors, V1 through Vn. And let's say the images are fairly uncorrelated, like these are random images on Instagram or something. So at the pixel level, they're fairly uncorrelated. So you would imagine that, you know, inner product is small. You know, we are rescaling them to be between -1 and 1, the pixels. So the expected inner product, you can imagine, is 0, and even for most pairs of images, the inner product is small. They're fairly uncorrelated. So now we're given a sparse combination, sum of lambda IVIs, where we know only k of the coefficients are non-zero, right? And they're all roughly the same. Let's say they could be even the same. Now it's easy to see that if epsilon is fairly small, by just doing inner products, you can start guessing which vector was in the combination. Like you go through all these n vectors, so it's linear time, not quadratic or n to the k, and do inner products with u, this sparse combination. And it's easy to see that this inner product is large in magnitude if and only if lambda I is non-zero. So you just go march through all the n images and compute inner products with u. And wherever you see a large inner product, that's the one that's in the sparse combination. Okay, so that's kind of a tag. It's not very, I mean, it requires going through this large data set, but still, it's some kind of attack. There are other kinds of attacks, you know, like if you're going to use mixed-up samples, and this is just mix-up, right? So no random mask. Now, the same kind of phenomenon happens. If I mix up the same image twice, right, in different epochs, mix it up differently, then, you know, this inner product kind of calculation, you can see whether two mix-ups contain the same image or not. Like if they don't contain the same image, the inner product is small. It says you're 0, but the expectation is small, but with high probability it's small. And if they contain the same image with high probability, it's large. So it's not just expectation, it's actually high probability. I took the slides from Yang Sebo. All right, so if you can, by this kind of inner product attack, you can start detecting which mixed up images contain the same underlying image. And now you can just average out and get, you know, even if you're mixing up 8 ways or 4 ways, you can average out those images which contain the truck picture and start reconstructing the truck. And there's a similar kind of attack that works against the public data set as well. But again, it has to run through all possible images. Notice that here on the left, all these images are training images. So you don't know the set of images. But with the inner product attack, you can see which pairs of mixed up images contain the same underlying image, the truck. And if you just average them out, you start seeing the truck. Okay, and this one is over the public data set. So it requires going through, you know, all of ImageNet or whatever. So that's not very efficient. But this is very, very efficient. Okay, so I'm ready to conclude. Instahide encryption was described, you know, which is a way to encrypt images. And then you can just do standard deep learning. It seems to effectively add information about encrypted image. We will, I forgot to say this, we will release a challenge data set very soon with the archive paper. And we just put it online on GitHub. And people are welcome to try to break our encryption. Okay, and this is a normal way in cryptography. You come up with a new encryption, you leave it out there, and people try to break it. And if it's not broken for a few years, then you start getting, or even a few months, you start getting confident that it's actually fairly secure. Okay, the magic here, again, was discussed in the Q&A already. This is magic, that you can take these really random looking images, albeit labeled, and do standard deep learning, and somehow the deep learning makes sense of those images and learns to classify. It's just another magic of deep learning out of, you know, the long string of magic that we've seen in the past 10 years. Further work, you can try to do extensions to more complicated data sets. You know, we just did CIFAR10 and CIFAR100, so you can try medical data sets, you know, all kinds of other things. Text data, adversarial robustness. This a priori is not clear it's relevant, but actually it is. Some of these ideas are very relevant, and there are papers forthcoming, which I won't talk about. Better analysis security. You know, if there are any cryptographers in the audience, you know, you've seen lots and lots of theory of crypto, and it's very tied to discrete settings. And there's solid reasons for it, for some of the reasons I alluded to, instant citing. And cryptography over real numbers is a long-standing dream, which has never been realized. And some people think it will never be realized. But at least this paper suggests that there's some weak form of encryption possible over real numbers, which is nevertheless very, very useful. So I hope there'll be much more theory, much more new ideas here, because cryptography is full of amazing ideas, and maybe some of that can be done efficiently over real numbers, and would be very useful in machine learning. Stop here. Thank you very much, and there'll be a blog post on my usual blog within next week. Thank you very much.
All right, thanks for the thought-provoking talk. Any questions? I guess maybe I'll just try to address all the questions that came up during the talk. Just give me 1 second here. Okay, so the first question is, I guess, relates to this contrast between differential privacy and Instahide. And the question is a bit high level. So the question is from Tan Lam. And so is this comparison a bit unfair to differential privacy? Is there a better baseline to compare with if differential privacy is not the right baseline?
Okay, so there's always a baseline of full strength crypto. You can use fully homomorphic encryption or some weaker form that suffices for deep learning. And that'll give you no accuracy loss, right? Because you're doing the actual deep learning on the actual data, but it's all encrypted. So that has no accuracy loss. So I didn't even put it in the table. I mean, that goes without saying. The trouble is that it's all the reasons I said, that you do the standard crypto, you need special hardware, special infrastructure, and all that. So that's the one. But otherwise, I'm not aware of any other privacy ideas. There's crypto, and there's differential privacy. Does the questioner have any other ideas like that's used for privacy?
Okay, thank you. The next question is from Varun, who asks, what if suppose the public data set is actually small? Would this scheme work?
I guess the question is, are the security guarantees, do they still hold if the public data set is very small?
Yeah, so,
also very small.
So the amazing thing about crypto is, it's all unprovable anyway, right? So you can make that assumption as well, right? I mean, so you're asking me whether I think it holds, right? Whether I have attacks. I don't have any attacks, because the attacks, I think, will, at least the current ones, fail even with very small numbers. So it's possibly secure. But if you want encryptions to stand the test of time, it's always a good idea to build in some scale, I think. Did I answer your question?
Yes, sir. Thank you.
Okay. The next question is from Dan Yan Zhuo. The question is, why is the sign flipping requires? Isn't the mix-up already enough for privacy?
Oh, I addressed that a few slides ago, right? Mix-up is not secure. Maybe the person signed in recently. I don't know.
Perhaps.
Yeah, it was. Yeah. This I described the experiments, and this was the theory.
Mm-hmm. Okay, let's see. Let me just try to find the next question that hasn't been answered.
People can unmute themselves too if they like and ask questions. I don't know what time it is. If we
have plenty of time, 23 minutes left.
I have one more question, Professor. Do you have any theoretical insight on why, like, training on these noisy images results in any usable model? Like, your co-author basically said that empirically you can see that it works on CIFAR if you randomly flip the sign, but anything deeper than that?
Okay, so I don't know how many people here have heard of phase retrieval. Sine flip is kind of like phase retrieval. That you're telling the net to ignore the magnitude, of, the sign of the pixel and just look at the magnitude. So there's a small number of possibilities, right? 2 possibilities. And if you look at, the RGB values, then 7 possibilities. So somehow all those possibilities are there for every pixel, and probably there's some correlation among neighboring pixels. I mean, we don't see any with the immediate neighbors, but if you go distance, up to a ball of radius 5 or 10 in the pixel space, there's probably some correlation, weak, but not very apparent. And then those local correlations have to be somehow, there's still ambiguity, and that local ambiguity has to be somehow globally disambiguated. I don't know if any of that made sense. And somehow deep nets are able to do that. And why is a mystery. I don't even understand why Mixup works. I mean, I was hoping to understand why Mixup works. That's the kind of thing we do in theory deep learning, or try to do. But yeah, this is another level with the Sine Flip.
Okay, so the next question is from Matthew O'Kelly. I think the question is asking if you were to assume some structure in the images, so I suppose piecewise smoothness or something like that, it is possible to recover images with randomly flipped. Suppose.
No, smoothness. Oh, I see. The neighboring pixels are the same. Yes, yes. So if you just blow up each pixel into 16 pixels, right, locally, yes. Then averaging you would. By averaging you would. No, averaging, it's multiplicative. Averaging. No, even then it's not clear. I mean, this works for MNIST, for example. Yeah, so no, it's not clear actually. I mean, it's plausible, but that's doable, but it's not clear because this works with MNIST as well, which I would say is fairly smooth, right?
Okay, thank you. And then the next question is, suppose this has been answered during the talk. The question is from Shumo Chu, is random sign flipping using the same key across all the training images? And suppose the answer is no.
Yeah, no. You use a new key, even for every epoch. So for every input, you change the key during the epochs.
Okay, so the next question is from Sharan Waswani. So the question is, suppose we use simpler models like just over-parameterized linear regression with an easy and synthetic data set, and then use the same mix-up plus Sine Flip idea. Is this magical property still true? Just trying to see.
Yes, yeah. So with linear regression, under some assumptions, like for linear models, you can show things.
Right.
It may even be in the appendix. I think well, the paper is not out. I think we have a section in the appendix noting this. For linear models under some assumptions, you can prove.
Okay. The next question is from Shima. And then the question is, what is the difference between Instahide and adding random noise? I suppose just adding.
Let's see if I forgot to point this out. Let me see if this was there. Oh no. Okay, I didn't put it there. All right, so yeah, so if you look at the amount of implicit noise in Instahide, right, like just in the mix-up, there's a lot of noise. If you add that much noise, the accuracy drops a lot. Was that the question? Like if instead of mix-up, you use noise, mix with noise, and then do the the sign flipping. Yeah, this accuracy drops really to useless levels. Yeah, I thought I had a picture on that. Maybe I've, okay. Yeah.
So the next question is, so this is asking about applications to text. So this question is from Abhishek Panigrahi. And the question is, if we were to apply Mixup to text data, we will break the structure, syntactic, and semantic structure of sentences. Should we still expect to get a good model on text data using it?
Yeah, so I don't want to talk about the text paper, as I said, yeah. For reasons I mentioned, yeah, it's in submission, it's submitted and in review.
Okay,
but yeah, I agree. That is why it wasn't immediate. That's why it's a new paper.
Thank you. The next question is from Antavia Batz. The question is Mixup here just for the augmentation to increase the accuracy, or will just flipping the sign also work well? For example, achieving performance within 5% of the Mixup.
Oh, just the mask alone? That's a question, right?
I suppose the question is, if you were to compare, let's see, if you were to compare the accuracy of the model with and without Mixup, would you expect to observe an increase in accuracy of just applying the Mixup? So is the
okay? So there's two types of Mixup in the scheme. So there's Mixup within the data set and Mixup with outside the data set with the public images. And within the data set is kind of like data augmentation, and that helps. And outside the data set, the public images, that hurts a little bit in the experiments. It hurts the accuracy.
Sanjeev, I guess the question is, how about just using the mask, not mixing? I think you can go to the next slide, and we have to record k equal to 1, and that answers the question.
Oh, yeah. Oh, that was a question. I see.
Yeah.
So you don't mix and just k equals 1. Yeah, good. So that's this question. Any other questions?
Okay, I think we finished all the questions in the chat box. Anybody have any live questions? If you do, feel free to raise your hand and I'll call on you to unmute yourself. Okay, maybe I'll start with one question.
Okay.
So if you were to consider a public data set that just consists of all the basis vectors, would this be just the same as a one-time path? So everything is random and then there's no structure at all?
No, the public data set has what vectors?
So
one-hot vectors.
All the vectors.
No, that doesn't mix very much, right? It only affects k pixels if you take k public images.
If you only take k, okay, right.
Yeah, that's not a very good idea.
Okay. Now, let's see. Do we have any other questions?
Yeah, I guess the other questioner who asked about mixing with noise, that's a little bit like in your setting would be your public images are just n random vectors, right?
Mm-hmm.
And mixing with that is not a good idea. It drops the accuracy.
Okay, I guess there aren't any more questions. So that concludes today's seminar. Let's thank Sanjeev again for the very inspiring and surprising talk. Thank you very much.
Okay, thank you.